Okay, let us start with the depth first traversal. Okay, so here we will state the algorithm in a way very similar to the way it is in trees, but we will improve it later to make sure it will work with graphs as well. So depth first traversal algorithm, it basically means that each vertex V is visited, and then each unvisited vertex that is adjacent to V is visited. So if you repeat this recursively, you will find that you will visit all the vertices. Okay, and it's going to be in depth first order. Okay, so this method can be implemented either using recursion, as we saw in trees, or it can be done with a loop with the help of stack. Okay, as you remember from our recursion lectures, you can usually convert a recursive method to iteration in some cases, but if you have to do that, then you must use a stack. Okay, so here is the iterative version that uses a stack. It says, so first of all, we create a stack, an empty stack, and then push the starting vertex onto that stack. And then we repeat as follows. While the stack is not empty, pop a vertex from the stack, call it V. Okay, if that vertex has not yet been visited, this is very important, because if it is visited and you're going to visit it again, then you will end up in a cycle. So if the vertex V is not already visited, visit it. So here it means you have to use some kind of Boolean array to keep track. Okay, now after visiting V, then you need to push the vertices adjacent to it onto your stack, and then you repeat the loop. So basically there are three things in the loop: pop, visit if not visited already, push the vertices adjacent to the one you just visited onto the stack. Okay, I'm going to show you a complete example, actually a number of examples, but one of them in showing the in animation form how this algorithm works so that you can understand it properly. But there's a note here. It says adjacent vertices can be pushed in any order. This last statement here, you see, after you visit a vertex, push the vertices adjacent to it onto the stack. Now, in what order are you going to push the vertices? Say vertex V has 3 adjacent vertices. In what order are you going to push them? Okay, so according to the algorithm, the order is not specified. However, normally we put a restriction to make sure that you get a unique answer. Okay, so here it says, to obtain a unique traversal, we normally push the vertices in reverse alphabetical order. Okay, assuming the vertices are labeled with letters A, B, C, D, so we put them in reverse alphabetical order. What does that mean? If the vertices adjacent to A, for example, are C and D, then we're going to push D first before we push C. The reason is that when we pop, C should come out first. Okay, so this is the idea. We will see this in a moment with this example. So we're going to take an example showing how depth first traversal work with this particular graph. Okay, so we are asked to start from vertex A. So the algorithm says, first of all, push the starting vertex onto the stack, and that's what we have just done. Then we're now going to start the loop until this stack becomes empty, and the loop has just 3 things to do. Pop a vertex, visit it if not already visited. So by visiting, we will just print it here. or write it here to indicate that we have visited it. Okay, 2, rather 3. So first is pop, 2 is visit, and then 3 is push the vertices adjacent to this vertex onto the stack. All right, so we're gonna pop A and visit it because it has not been visited. So we have done 2 steps in that loop. Next is to identify what are the vertices adjacent to A. Okay, I have marked them here for you. There's AB, AE, and AD. So these are the vertices adjacent to A. So what we will do is we will push each of them in the stack. But in what order? We are interested in visiting the vertices alphabetically. Therefore, since we know the last one to enter the stack is the first one to come out, we're going to push them in reverse alphabetical order. So E will go in there first, then D, then B. Okay, so this is the order we're going to push them. So this is the first iteration. Then we repeat. Pop, visit if not visited, and push the adjacent vertices. Okay, so we're gonna pop B from the stack, visit it since it has not been visited, and make it to be our active vertex. So our current active vertex is B. The next question is, what are the vertices adjacent to B? We have C and we also have E. Okay, now notice the algorithm didn't say push only if not push before. Okay, there is no restriction. So the only one we cannot push is A because it was visited before. Okay, so the vertices of B, rather the vertices adjacent to B not yet visited are C and E. Even though we push E before, that is not an issue. We're going to push it again. Okay, we will see that there is no problem because when we pop, we don't visit directly. We have to check. If a vertex was visited before, we don't visit it again. Okay, so we're going to push again in reverse order, E followed by C. Okay, so that is the end of our second iteration. Next, we pop C and visit it, and it becomes our active vertex, and identify its adjacent vertex not yet visited, only F this time. So push that F onto the stack. Okay. Next, we pop F, visit it because it has never been visited. But this time, F has no adjacent vertex that was never visited before. The only adjacent vertex we have is C, but C has been visited. Okay, so that will be the end of the iteration at that point. We just need to go back to the beginning of the loop and pop the next element, E. Okay, so E was never visited, so you're going to visit it and make it to be your next active vertex, and identify if it has any adjacent vertex not yet visited. Okay, it has 3 adjacent vertices, A which has been visited, B which has been visited, and G which has not yet been visited. So actually it's only G that is left. So we're going to push G onto the stack and make it to be, okay, so there, and then repeat the loop. So we pop G, visit it, and make it to be our next active vertex. Is there any adjacent vertex of G not yet visited? Yes, there is D and there is also H. So push them in reverse order. H first, followed by D. Okay, and then go back to the beginning of the loop, pop D and visit it. This time you will see that D has no adjacent vertices not yet visited. Both G and A were visited before. So just go and pop the next one, H, and visit it and make it to be your next active vertex. Does it have any adjacent vertex not yet visited? Yes, there is I. So we identify it and push it. Okay. Next, we pop I and visit it. Okay, and make it to be our next active vertex. This time I has no vertex not yet visited. Okay, so we go ahead and pop D. However, remember, when you pop an element, you have to check if it has not yet been visited. In this case, D has been visited before. So when you pop it out, just throw it away. So D will be popped and thrown away. The same thing here, E, when we pop, we have to check, has it been visited? Yes, it was visited before. So don't visit it, just throw it away. Okay, and now the stack is empty, so our traversal will terminate. So basically, this is the order in which the elements are going to be traversed using depth first traversal. Okay, these numbers here are telling you the number of, or the order of traversal. Okay, so with the stack, you can easily find out the list in which the vertices of the graph can be traversed using this method. Now here, there's an important point I want to mention, that although if you use a stack, you will never go wrong, you will always be able to find the list. For this depth first traversal particularly, you can actually do it directly, even without using stack. You can do it mentally. How? Here is how. Start from the vertex that is given to you as a starting vertex. Normally you will be told where to start from. And then keep going through the vertices, following the arrow alphabetically. But whenever you get stuck, then you backtrack and see if there is an alternative route that you can follow. So let's go from A, alphabetically we go to B. Okay, as you can see here, A is to B. From B, alphabetically we go to C. So again, you can see C. From C, alphabetically we go to F. Okay, so A, B, C, F. But now we are stuck. From F, we cannot go anywhere. So you have to backtrack. Now when you backtrack, you're going to follow the same path that you followed to reach where you are. So we go back to C and ask, is there any other route to follow? No other route. So backtrack back to B and ask, is there any other route to follow? Yes, there is. We can go to E. So from B we go to E. As you can see, E is the next element to visit. Okay. From E, is there any other place to go? Well, we have already visited A, so the only other place is G. So go to G. Okay. Now from G, where should we go? Alphabetically, we can go to D. I mean, we have two options, either D or H, but D is the first one alphabetically, so we have to go to D first. Okay, so G to D. Okay, as you can see here. But now again, you are stuck because from D you cannot go to A. A was visited before. So what do? Backtrack to G and ask yourself, is there any other option? Yes, there is. You can go to H. So we go to H. Okay, and then from H we go to I. Okay, so actually it's easy to do this traversal mentally. Just follow the elements alphabetically. A to B, B to C, C to F, backtrack, go to E, go to G, go to D, backtrack, go to H, go to I. Okay, I'll show you two more examples in the next slide to emphasize this mental way of doing it. Okay, now but this let's go back to our points earlier that says you have to be careful for a graph that has disjoint subsets or isolated vertices. Okay, if you just follow the algorithm as we just saw it, we will never be able to visit those vertices. So you will actually have to repeat the traversal starting from each unvisited vertex until you visit all the vertices. So we're going to see an example. Okay, so this is the modified algorithm basically. This inner loop or this inner part is the same algorithm that we saw before. We are now adding an outer loop to make sure we visit all the vertices. So it's saying for each vertex V in the graph, take that V to be your starting vertex and do the traversal. When you finish, go back and take the next V. If that V has been visited, no need to do anything. Okay, but if not, repeat the traversal from the new vertex. So in other words, by the time you finish this loop, you will have visited all the vertices, because this outer loop says for each vertex V in the graph. Okay, so just this outer loop you need to add to the original algorithm that we saw earlier to make sure it takes care of disjoint subset. So to see what this means, let's take this graph. Now this graph looks like it is two graphs, but actually it's one graph. It's just that it is disconnected. So we're going to start our traversal from A. Okay, we're going to do it mentally. So from A, we go where? Alphabetically, we go to E. From E, alphabetically, we go to F. From F, alphabetically, we go to I. Okay, so far we have done A, E, F, I. But here we're going to get stuck, nowhere to go. So backtrack to F. Again, no other option because we have already visited both A and E. So backtrack to E. No other option. Backtrack to A. No other option. And this time there's another option. Go to G. And then go to B. Okay. Now, so if you notice the path that we actually follow to do the traversal is A, E, E, F, and F, I, and then A, G, and G, B. But at this time, you're going to get stuck. Okay, no other place to visit. So we're going to go back to the outer loop and try it starting from each vertex. For B, E, F, I, and G, we will see that they are already visited, so we will not do anything. But when you reach E, or rather when you reach C, you will see that you have not yet visited C. So you're going to start another traversal from C. So C will take you to H, and H will take you to D. This is the graph that shows you the path that you actually followed in doing this traversal using depth first. So as I mentioned here, of course the first element we visited was A, then E, which is number 2, then F, which is number 3, then I, which is number 4. Then we backtrack, and then went to G, which is number 5, and then B, which is number 6. So at this point we got stuck. So we start another traversal from C. So this was number 7, then H, which is number 8, and then finally D. So this is the order of the traversal in this case. The solid lines are showing you the path that is actually followed in doing the traversal. Okay, now let us look at breadth first traversal. Okay, The difference with breadth first traversal, as we recall in trees, after you visit a vertex, a node in that case, in the case of tree, we have to visit all its adjacent vertices before going down, because we're going to look at it like level by level, level by level. So the method can be implemented using a queue rather than a stack, and a Boolean array is used to ensure that a vertex is visited only one time. And this is the algorithm. So again, this is the simpler version of the algorithm. Later on, we're going to add a loop at the top to ensure it is repeated for each starting vertex. For making each vertex to be a starting vertex, to ensure that isolated paths are also visited. So it's very similar. The only difference is, there are two differences. Of course, we are using a queue. So that is one difference, whereas the other one is using stack. Okay, so it says enqueue the starting vertex. And then it says, while the queue is not empty, dequeue a vertex from the queue and visit it directly. See here, it didn't say if not visited. Visit it directly. Dequeue and visit. No question asked. Why? Because this last line is different from the other algorithm. It says enqueue vertices adjacent to V that were never enqueued before. So this time, different from that were never visited. Okay, it's not only if they were not visited, if they were enqueued before, we don't enqueue them again. So there will be no repetition in the queue, unlike the other algorithm where there was repetition in the stack. So because of that, when we dequeue, we just visit directly, because we guarantee that the vertex that were enqueued were never enqueued before and were never visited before. So just dequeue and visit and enqueue vertices that were never enqueued before. So again, we're going to adopt a modification to ensure that you get a unique result, which is that vertices that you enqueue here are going to be enqueued this time in alphabetical order, not in reverse alphabetical order, because we know in queue, the first to go in is the first to come out, so there is no need to enter the element in reverse order. Just put them in alphabetical order. Okay, so like we saw with the other algorithm, we're going to take the same example, but this time solve it using breadth first traversal. Okay. So we enqueue the starting vertex, that's what the algorithm says, and then start the loop. Okay, dequeue and visit directly. Dequeue and visit. And now enqueue the adjacent vertices that were never enqueued before. So the adjacent vertices of A are B, D, and E. Of course, none of them was enqueued before, so just enqueue them. So we enqueue B in alphabetical order, and then D, and then E. Okay, and then repeat the loop. Dequeue and visit B directly. Okay, identify its adjacent vertices that were never enqueued before. Okay, you can see it is adjacent to E, but E was enqueued before. Okay, so was A. A was enqueued before, in fact, even visited. So we don't enqueue A and E, only C we're going to enqueue. Okay, so enqueue the C, and then repeat the loop. Dequeue D and visit it and make it to be your active vertex. Identify any vertex of D, adjacent vertex of D that is not yet enqueued. Obviously, we have not yet enqueued G, so we're going to enqueue G. Okay, and then repeat the loop. DQ the front element, which is E, and visit it directly and make it to be your next active vertex. See if there is any vertex that it is yet to any adjacent vertex to E that was never enqueued before. This time there is none. B was enqueued, A was enqueued, and even G was enqueued. Okay, you can see G is in the queue. So nothing to do, just go and dequeue the next one and visit it directly. Now at this point, I want to show you why this traversal is considered to be breadth first, or what we call level by level in trees. See, when we visit a vertex A, we have now visited all its children. We have visited B, D, and E. These are the children of A. So you can consider this as the next level. After A, this is the next level. Okay? So then now we can talk about the grandchildren of A, starting with the first son, B. You know, it has a child C, so this is considered to be level 3. So as you see, the next element we're going to Q and is C. Okay, E has no other grandchild, but D has G. So as you can see, as we have in the Q, G will be the next one. So this is how they are being visited level by level. However, unlike what we saw in depth first, it is really difficult to do this without using a queue. So even though you may force yourself to do it mentally, I suggest you don't. Just use a queue to do it. The one with stack is very easy. You will hardly make a mistake, but this one is easy to make a mistake. Okay. So anyway, the next item to dequeue is C. So you dequeue C, visit it, and make it to be the next active vertex. The only adjacent vertex of C not yet visited is F. So identify it and enqueue it, enqueue the F. And then repeat, dequeue G and visit it and identify adjacent vertex of G not yet enqueued, only H, because D was enqueued and even visited before. So only H, enqueue the H. Okay, then repeat the loop, dequeue F and visit it. Okay, does F has any adjacent vertex not yet visited? None at all. Okay, so just repeat the loop, dequeue H and visit it and identify if it has any adjacent vertex not yet visited. Obviously I. So enqueue the I. Okay, and then repeat the loop, dequeue from the queue, we're going to dequeue I and visit it, and at this point I has no element and no vertex adjacent to it that has not yet been visited, so we are actually done. Also, if you check the queue is empty, so the loop will stop. So this is how to do breadth first traversal of graph using a queue. It is really level by level. If you consider this as the root of your tree, then this followed by the immediate children, followed by this C and G, followed by F and H, followed by I. Okay, yeah, I hope this explains it. Now, just like we saw with the depth first, if your graph has disconnected components, then the simple version of the algorithm we saw there will not work. You will have to use an outer loop to make sure you don't just start from one vertex, you start from each vertex in the graph. If you do that, you will be able to visit all vertices. So this is what this example is showing you, exactly like we saw with the one on depth first, and this is going to be the result. Here you will see a difference. When we visit A, we have to finish with all its children, which are E, F, and G. So as you can see, the order here is okay. So yeah. So after visiting A, we will do E, which is number 2. We will do F, alphabetically is number 3, and we will do I. Actually, is also directly connected. So we'll do I as, but before I, we do G. So alphabetically is G next. Okay, and then I. So this is how they will be visited. All the children of A must be done before looking at the grandchildren. So from A, we go to E, then we go to F, then we go to G, then we go to I. So now that we are done with the children of A, we can now look at its grandchildren. All these three don't have any children, so only this G has another child, which is B. So it's going to be visited. So at this time, you're going to get stuck. But because of the outer loop, we will be able to reach C and visit it. And then look at its child. Okay. And then look at the grandchild. So this is the order the elements will be visited using breadth first traversal. Okay, so actually this is showing you the same idea, but for a directed graph. Okay, the other example was showing you undirected graph. This is showing the directed one. The idea is the same. All right. You just make sure you follow the arrows. For example, here from A, we cannot go to I. Our only option are E and F. So E is going to be number 2 and F is going to be number 3. Okay. And then the children of E, which is only I, will be number 4, and so on. So this is just the difference between this example and the previous. Okay. So this is basically about graph traversal. The last topic in this lecture is about shortest path algorithm. The shortest path algorithm is applicable to age-weighted graphs, graphs for which the ages have some weights. Okay, and the idea is to find the cost of reaching all the other vertices from a single source. Okay, so let's go through the points. So for example, in a graph representing a network of airports, the weight that is attached to an edge could represent either distance from one city to another, or in terms of money, how much it will cost you to go from one city to another, or time, how long it will take you from one city to another. Okay, so the value you attach to the weight could differ, but in all cases, the objective is to find the shortest path. So, for example, what is the fastest way? If your parameters are time, what is the fastest way to reach from A to B? Or if your concern is the cost, what is the least expensive route to follow from A to B? And finally, it could be distance. Okay, for example, if you are traveling from Jubail here to Dammam, your concern may not be the distance, but maybe the money, because there are many cameras on the road. So if you follow the main road, there are obviously many cameras, and if you are the type that will speed, you will definitely be caught by cameras, so you will pay more. You may prefer to follow a route that doesn't have camera, but it's a more distance route. Okay, so you may not worry about the distance, but you are worried about the cost, something like that. So it depends on the problem you are solving. But what we are saying here is either way, all of this are actually an instance of the same problem. What is the shortest path? Okay, the unit that you attach to the distance could differ, but it's the same problem. So the unit could be in terms of distance, could be in terms of money, could be in terms of time. Okay. So here we are trying to answer, is the shortest path problem well defined? Can it be solved? It says here, if all the edges in a graph have non-negative weights, so they all have 0 or positive values, then it is possible to find the shortest path between two vertices. Okay, for example, in the following graph, the shortest path from B to F, here, is not what you think, because what you think may be B, C, E, F. This seems to be shorter in terms of distance, but count the cost and see. 5 plus 4, 9 plus 1, 10. The actual shortest path is through A. B, A, C, E, F. B to A will cost you 3. To C cost you so far 4. And then to E cost you so far 8. And then to F costing you 9. So this is the shortest path based on the values we have here in the graph. So this is the idea of this problem. If the weights here are non-negatives, then the problem can be solved. So that's what we are saying here. That the problem is well defined for a graph that contains non-negative weights. I don't want to go into detail about it, but actually even for a graph that has negative weights, as long as they are not involved, those negative weights are not in a cycle, like this is a cycle. So if this is negative, I want to reduce the cost, just go a number of times across this cycle, and I will get a smaller value if the sum total of the cycle is negative. Okay. But anyway, the problems we will be concentrating on are those with positive values of the weights. So we will not be affected by this definition of whether the solution exists or not. If the weights are positive, definitely the solution exists. And this is the algorithm we are going to use to solve this shortest path problem. It is devised by a guy called Dijkstra. So it is called Dijkstra's algorithm. The algorithm solves a single source shortest path problem for a non-negative weight graph. So you give a single vertex and you want to know the shortest path from that vertex to all the others. Okay, it finds the shortest path from an initial vertex V to all the other vertices. And this is the algorithm. The algorithm receives this input, a weighted simple graph. Okay, actually it can be directed graph. It's a weighted graph and a starting vertex. Okay, then it proceeds as follows. First, it assumes the distance from the source to all the others is infinity. You remember when we are trying to minimize, we initialize our value with the maximum possible so that when we find a smaller value, we update. So initialize the distance to all the other vertices to infinity. Okay, then we initialize the current distance of this to the starting vertex to 0, because we are already there. This is the starting vertex, so its current distance is 0. Okay, mark all the remaining vertices as to be checked. We have not checked any, so they all becomes you put them all in a set called to be checked. Okay, then now you repeat the following loop for as long as there is a vertex to be checked. There is a vertex in this set that has not yet been done. Okay, so what do? You find the minimal cost, okay, from all the elements in to be checked. Which one has the smallest cost? Call it V. Okay, this V you assume is the minimal for that particular vertex. You cannot get any smaller than that, so you're going to remove it as having done. We have finalized. This is the smallest distance we can get for this particular vertex. Okay, and now you need to update the distances from that particular vertex to all the others. Okay, so for all vertices U adjacent to V that are inside to be checked, you compute the distance from U to that vertex plus the current distance of reaching V, which you have just finalized. If you find that the current value for U is more than this summation, then you're going to update the distance of reaching U to be these two values, the cost of reaching V plus the weight from U to V. Okay, and you also you update the predecessor from which we're going to reach U to be V. Okay, this will be more clear actually when we take the example. So we will see a full example, actually two examples. One of them I will show you in detail using animation, and the other one I will make it a little simpler. Okay, now but before we take the example, this is a simpler version of the algorithm that work with a table, okay, to trace the execution of the algorithm. Okay, it says in your table, where I will show you the table in a moment in the example, initialize the distance to the starting vertex to be 0, because we are already at the starting vertex, so the distance to reach it is 0. But for the others, we initialize the distances to reach them as infinity, since we don't know the distances to reach them, much less about the shortest distance to reach them. Okay, now we repeat the following 4 statements until all vertices are finalized. 1. You take you finalize the cost and predecessor of the vertex V with the smallest cost from those that you have not yet finalized, because after each loop here we will be finalizing one vertex. So from those that are not yet finalized, take one of them, the smallest, the one with the smallest distance, and finalize it. Okay, also since we have finalized it, we will be able to finalize its predecessor, meaning from which vertex do we reach that particular vertex to obtain that particular minimal cost. Again, this will become clearer with the example. Okay, so once you finalize the current one of the vertices, now make it to be your next active vertex. So assume now you are not at the starting vertex, but at this vertex V that you have just finalized. Ask yourself, where can you reach from V? Okay, and then compare the cost of each vertex U reachable from V that is not already finalized. Compute its cost as the cost you have just finalized for V plus the weight of reaching from V to U, to that particular vertex. If this sum is smaller than the current cost of reaching U, then you're going to update the cost and also update the predecessor to be V. Okay, so you will do that only if this sum is less than the current value. Okay, for those vertices that are not yet, that cannot be reached from V, you will just copy their current distance to this particular column that you are working on, and then repeat the process. This is what I'm going to explain. So I'm going to be following this algorithm in the example I'm going to show you. Okay, we're going to use a table like this. In an exam, normally you will be given this table. So for this particular graph, normally again you will be told which vertex is the starting vertex. Okay, so here it says trace the execution of Dijkstra's algorithm for the following graph starting from vertex B. So this is our starting vertex. Okay, so this table is going to be given to you. As you can see, it has a column where all the vertices are listed, in this case A to F. A column where we're going to do some repetitions. So how many repetitions? Depend on the number of vertices. Here there are 1, 2, 3, 4, 5, 6. So there are going to be 2 loops. 6 iterations. Okay. There is a column where we will give the initial values of the costs. As we just mentioned before the loop in the algorithm in the last slide, the cost of the starting vertex will be 0, but for all others, initially will be infinity. Okay, so in each iteration, we will be finding one minimal value, finalize it, and identify its predecessor. Make it to be the next active vertex and repeat the process until we finish. Okay, so this is the table. You can be guaranteed that this table is going to be given to you. So the first step, according to the algorithm, initialize the cost of the starting vertex to be 0. And for the vertices that we don't know, we put infinity. For all the other vertices, put infinity. So this is all before the loop. Now in the loop, we're going to be doing 4 things, as I said. First, identify among these values which is the smallest. Obviously 0 is the smallest in this case. So finalize that particular cell. There is no better way of reaching B than 0. 0 is the smallest value. So we're going to finalize the cost of reaching B. Okay, remember the purpose of the algorithm is to find the cost of reaching from B to all the others. So what is the minimal cost from B to A? What is the minimal cost from B to C? What is the minimal cost from B to D? And so on. From B to all the other vertices. This is our target. So far we are saying from B to B is definitely 0 because we are already there. So that is step number 1. Finalize that vertex. In this case, there was no predecessor. We didn't come to B from anywhere. This is the starting vertex. So just put a dash for the predecessor that give you this minimal value. Okay. Next is this one that we have just finalized. Make it to be our next active vertex. So here in this column, we will be storing the next active vertex. So B become our next active vertex. Now, when you have an active vertex, you're going to presume you are there. So suppose we are in B. You will ask yourself, where can you reach from B? Obviously, you can reach A with the cost of 0 plus 3. It costed you 0 to reach B, plus the cost of reaching from B to A, which is 3. So it will cost you overall 3 to reach A. Now you're going to compare this new value against the current value of reaching A. If the new value is smaller, then you're going to update the new value and put it here. If it is equal or not, you don't accept. You only accept if the new value is smaller. So obviously, 3 is smaller than infinity, so we're going to accept a new cost for reaching A to be 3. We can equally reach C from B with a cost of 0 for reaching B plus 5. So that's 5. Again, you can see the current cost of C is infinity. Definitely 5 is smaller than infinity, so we're going to accept the new value. Okay, so this is step number 2. Step number 1, finalize the current minimum and its predecessor. Step number 2, identify, make the one you just finalized to be your active vertex, and compute the distances and see if you can get a smaller value. If that is the case, update the new distances. Now, for those vertices that we cannot reach from B, we cannot reach D, we cannot reach E, we cannot reach F. Okay, from B, there's no direct edge to E or D or F. Just copy their current value from the last column to this column, because this column has to be complete before we can consider that we have finished with this iteration. So just copy the 3 values of D, E, and F to the next to this particular column, and we can consider now and say we are done with iteration number 1. To start iteration number 2, again you look at these values and see which is the smallest. Obviously 3 is the smallest. So as a first step, you finalize it, meaning there is no need to check again. There is no smaller value to reach A better than 3. To reach A from B, there is no other way to reach A that can give you better than 3. So we conclude, nothing to do again for this particular vertex. Okay, what is the predecessor? The predecessor is the vertex from which you get this value. Obviously, we got this value from B. Usually, you can just look up and see it was B that gave you this 3. So B is the predecessor. We're gonna need this predecessors later when we wanna draw the resulting graph. Okay. Step number 3, make this vertex that we have just finalized to be your active vertex. So A is our next active vertex. And ask yourself again, from A, where can you reach? In this case, only C. There's only an arrow here from A to C. Okay. So the question is, what is the cost? Now here you have to be careful. We are looking for the cost of reaching from B, not just from A to C, but from B to C. So you have to add at what cost did you finalize A? 3. The minimal cost of reaching A was 3. So now you have to add that to the distance from A to C. So 3 plus 1 is 4. So the new cost of reaching from B to C is 4. The question is this 4 better than the previous value? You can see the previous value was 5. Okay, if we went directly from B to C, it would cost us 5. But now, coming from A, it will cost us 4. So since this value is going to be smaller, you're going to update. So update and say the cost of reaching C is now 4. Okay. At this point, if you wish, you can put the predecessor, but we're going to do it later. So C is the only vertex you can reach from A. Therefore, you just copy the values of the other vertices. We still cannot reach them, so they are still infinity. Okay, so that brings us to the end of iteration number 2. To start iteration number 3, again you repeat the process. Which value among these is the smallest? Obviously 4 is the smallest, so finalize it. Okay, you can blank out the remaining cells. The value is not going to change. What is the predecessor? A. It was coming through A that gave us that value 4. So the predecessor is A. Okay. Next, make C to be your next active vertex. So we're going to position ourselves now at C. Suppose we are at C, where can we reach? This time we can reach 2 places, D and E. Okay. Now we will be adding the cost that we finalized for C, which was 4, plus the distance from C to D. Okay, in this case it's going to be 6. 4 plus 2 is 6. Okay, the present value of D, or the present cost of reaching D, is infinity. Obviously 6 is smaller than infinity, so you're going to update. Okay, similarly here, the cost of reaching C was 4, plus the distance from C to E, another 4, total is 8. So 8 is better than infinity, so again you're going to accept it. Okay, we still cannot reach F, so we just copy its previous value, infinity. And that brings us to the end of iteration number 3. Next, again, we look at this and see which is the minimal value. The minimal value is 6. So mark it and finalize that row. We will never get a smaller value than 6 to reach D. What is the predecessor? Predecessor is C. We got this value of D coming from C. So the predecessor is C. Usually you can look up to find it. There are cases where the looking up may not work. I will show you later in the next example. Okay. So having done that, what we put the predecessor as C, and then we make it to be our next active vertex. So D is the next active vertex. So position yourself at D and see where can you reach. Finally, we can reach F at the cost of reaching D, which was 6, plus 5, the distance from D to F. So that is 11. 11 is definitely better than infinity, so we update it. All right. What happened to this cell? We cannot reach E from D, so just copy the previous value. Okay, to complete this column. We always must make sure all elements are completed, even if it means copying from the previous column. Okay, so that brings us to the end of iteration number 4. And to start the next one, again we look at the 2 values that we have here. Which is the smallest? Obviously 8 is the smallest, so we finalize it. There is no better way of getting the cost of E better than 8. Now, here is a very important question. What is the predecessor? I was saying you just look up to get it, but actually in this case looking up will not work. We didn't get this 8 from D. We actually got it from C. So you have to go back and say, where did I get 8? Okay, this was where we got the 8. So that vertex is actually the predecessor, not the one directly up. So you have to be very careful here. So the predecessor was C. We got the cost of reaching E actually from C, not from D. We can never reach from D to E. Okay, so the predecessor was C. Okay, this is very important to take note because it's different from the other cases. Now, To start the next iteration, we make E to be our next active vertex, and we position ourselves there and ask from E where can we reach. We can reach F. Okay, what was the cost of E? The cost we finalized for E was 8. Now if you add 1 to that to reach F, we're going to get 9. Is 9 better than the current value? Obviously yes. Alright, so we're going to accept the new value. Okay, so that brings us to the end of iteration number 5. We try to do the next one by finalizing this single value. Nothing more to do. The predecessor was E. Now if you attempt to do another iteration from F by making F to be the next active vertex, you see that there is nowhere else you can go, and that is the end of the algorithm. So these cycled values are telling you the minimal cost of reaching each vertex, and these predecessors are going to help you to draw the resulting graph, to trace which path are you going to follow to actually achieve these minimal values. This is what we're going to do next. How do you obtain the resulting graph that will tell you not only the minimal value, but the path that was followed to obtain those minimal values? Here is how. First, you draw all the vertices of the original graph. No change in terms of the vertices. Okay, we still have A, B, C, D, E, F. But now, to draw the graph, you will draw from a predecessor to a vertex. So there will be an edge BA. Okay, there's an edge BA. Okay, and there is a cost 3 which we obtain for reaching A. So you also write that cost against A. Now notice here the value here is not the weight of this edge. It's a common mistake students make. It's the cost. Remember, the algorithm is to find the minimal cost of reaching from B to all the other vertices. So we are saying to reach A, the minimal cost is 3. Okay, so the 3 is on the vertex, not on the edge. This is why the resulting graph is called vertex weighted graph, not edge weighted graph. Okay, so that is the first edge. Next, well, for next vertex there is no predecessor, so just put the cost. Okay, the cost of reaching B is 0 because we were already there. This is the starting vertex. Okay, but for the next one we're going to draw an edge from A to C. A to C. So this is the edge, A to C. Okay, and what is the cost? 4. See, the cost is on the C. It is telling us the minimal cost of reaching from B to C is 4. How do we get it? By going through A and then A to C. If you go and add, you see that you're going to get 4. B to A will cost you 3, and then A to C will cost you 1. 3 plus 1 is 4. So the cost of reaching, the minimal cost of reaching from B to C is 4. Okay. Next is from C to E, from predecessor to a vertex. So we're going to draw an edge from C to D. Sorry, the first one here, C to D. Okay, C to D, I jumped that one. So C to D, the cost is 6. So you attach the 6 on the D. Okay, so again what you are saying is the minimal cost of reaching from B to D is 6. How do we get it? By following this path. B to A, which costs 3, plus A to C, which costs 1, so far 4, plus C to D, which will cost 2. So total is 6. Okay. Next is C to E. Okay. And the cost for that is 8. Okay. the cost of reaching C, which was 4 plus another 4 more to reach E. Okay, and finally an H from E to F, so E to F, and the cost is 9. As you can see, the cost of reaching E was 8 plus 1, that will give you 9. So this is the resulting graph that tells you the minimal cost of reaching each vertex from A. Not only that, it also tells you the route to follow to achieve that minimal cost. So to get a minimal cost of 9, we have to go through A, then C, then E, then F. This is basically what Dijkstra's algorithm is about. I'm going to take a more bigger example in the next slide to show you few cases that didn't occur in this simple example and how to deal with them. So this is our example number 2. It is much bigger. It has 10 vertices. Okay, as you can see in this graph, 6 plus 4 here, and the question says we should start from vertex D. Always you will be told which vertex to start with. So starting from vertex D, find the minimal cost of reaching each vertex. So although the graph looks big and complex, if you really follow the algorithm, it's very simple. I'm going to go much faster than in the previous example because I believe we are familiar with most of what you need to do. So the first thing is to initialize the cost of reaching D to 0 and the rest to infinity. That's what we have. Initially, the cost of reaching D is 0, all the others is infinity. And the algorithm simply says, determine which of this is the smallest, in this case 0. So make yourself there, so position yourself at D in this case, and ask yourself where can you reach? Well, we can reach A with a cost of 4, so 0 plus 4 is 4, and we can also reach H with a cost of 1. 0 plus 1 is 1. So obviously 4 and 1 are better than infinity. Therefore for A we will put 4, and for H we will put 1, but for all the others we cannot reach, so just put infinity. Okay, so this is what you have. Okay, after finalizing the 0 and making D to be your next active vertex, this is what you have. You have 4 to reach A and 1 to reach H. All the others we don't know. Okay, so the next thing is to look at this again and see which is the smallest. Obviously 1 is the smallest. So finalize the cost of reaching H as 1. We can never get a smaller value than 1. Okay, make it to be your next active vertex and position yourself at H and see where can you reach. We can reach E and I. Now remember, H costed you 1. So E through H will cost you 1 plus 5, which is 6. And also this will cost you 10. 1 plus 9 to reach I. So obviously this values, E is at present infinity. So obviously 6 is better than infinity, so we're going to change this one. Similarly, I is infinity. 10 is better than infinity, so we're going to change this one. But for the others, we just copy them from previous iteration, including the 4 here. Copy 4 to here, and then infinity, infinity. So this is what you have in that iteration. I don't have to do it one by one because I think you are now familiar with what we are doing. So you can see we have updated the cost of E to 6, the cost of I to 10. We copied the 4 from A from previous to here. And the rest, because we cannot reach, again just copy from previous column. They are all infinity. Good. We have also, this is important, we have finalized the cost of reaching H. Okay, so no need to change anything in this row. And the predecessor is D. That's why we got this one. So the predecessor is D. Good. So the next step is to identify among this which is the smallest. 4 is the smallest. So mark it. You have to be careful here. The predecessor is not H, it's D, because that was where we got the 4. Okay, but you're going to position yourself at A now and ask where can you reach. We can reach only E. Okay, we don't have to bother about H because H was finalized. Okay, so you don't look at it again. Once it is finalized, it's finalized. Khalas. So only E is our new value. And here actually there is a good development, because now if we come through A, which you remember costed us 4, we only need to add 1 more to reach E. That will give us 6. That will give us 5. 4 plus 1 is 5. Now if you look at the present value, it is 6. So this new value is in fact smaller. So we're going to accept 5 for the new value for E. All the others, since they cannot be reached from A, we just copy them as before. So this is what you have after finalizing A with the predecessor as D, as I emphasized. The predecessor is not H but D, where we got the 4. Only this value will change. 6 will change to 5. The rest of the values are only copied directly from the previous column. Okay. Now repeat the process. Among these values, which is the smallest? The smallest is 5. So we're going to finalize. The cost of reaching E is never going to be less than 5. So we finalize this row. The predecessor is A. That's where we got the 5. Okay. And then we're going to position ourselves at E. Okay. So if you are at E, where can you reach? Clearly, we can only reach F. Okay, it cost us how much to reach E? 5. So 5 plus 3 will be 8. Is the present value bigger? Yes, it was bigger. It was infinity. So we're going to replace the cost of reaching F to 8. And all the other values will remain as they are. Okay, so you see we put 8 here. The rest are infinity, 10, and 8. Okay, repeat the process. Among these values, which is the smallest? 8 is the smallest. So finalize it. Nothing more to do on this row. The predecessor is E. Okay, and now position yourself as F as your next active vertex. So suppose we're at F. This time we can do many things. Okay, if you are at F, you can now reach almost all the vertices. We can reach B, we can reach E, C, we can reach G, we can reach I. The only value or the only vertex that we still cannot reach is J. Type. So what are the costs? For B, remember the cost of reaching F was 8. So for B is going to be a plus 1, which is 9. For C is going to be 11. 8 plus 3, 11. For G is going to be 15, 8 plus 7. And for I is going to be 9. For J, it will remain infinity. So this is actually what we have. 9 for B, 11 for C, 15 for G, 9 for I, and infinity still for J. Good. Now this is one of the important points to highlight. Difference between this example and the previous simpler one. You may have two values to be the same, two minimal values or more. The question is, how do you know which one to take? Should you take them both? No, the algorithm says you should take one minimal value at a time. So we're going to take one minimal value. Now which of them? We will take the one that is alphabetically first. Okay, so we're going to minimize the value of B to be 9, and we're going to make it to be our next active vertex. Obviously the predecessor is going to be F, okay, and B is going to be our next active vertex, not I, even though I is also 9. Type. So position yourself at B, and you see that we can only reach C. Okay, so what is the overall cost of reaching C? Well, we finalize B with 9. Let me put the cycle there. So we finalize the cost of reaching B as 9. So therefore, the new cost of reaching C is 11. Now this is another difference between this example and the other one. We got a new value 11 for reaching C. The previous value was 11. Okay. The question is, should we accept this new value? The answer is no. We only accept a value if it is smaller. If it is equal or greater, we reject it. Okay. So here we will copy 11 to this cell. So you will see 11 here, but it is not because of this value, 9 plus 2. No, it's because of the previous value through F. Okay, through F, we were also getting 11. So in other words, when you are writing the predecessor, you don't take B to be the predecessor of C, even though this is the 11. We will take F to be the predecessor. In other words, we are rejecting the new 11. We are accepting the old 11. Okay, I hope this is understood. Okay, so C is the only value that we can reach, and which is not going to change. Actually, we're going to just copy the previous. So actually, in this case, after finalizing B, just copy everything from the previous column to the next. As you can see here, after making B to be your next active vertex, just copy the value. So this 11 is not being obtained by adding 9 plus 2. No, it is the previous previous one that we are just copying to the new column. Okay, also copy 15, copy 9, copy infinity. Okay, now repeat the iteration after identifying the smallest value. So among these values, 9 is the smallest. So we're going to finalize it with the predecessor as what? Not B, but F. This was where we got the 9. So the predecessor is going to be F. And you're now going to make it to be your next active vertex. So I will be here. Now, with I here, you will ask yourself, where can you reach? Again, as you can see from the graph, we can only reach J. So for the first time we are reaching J. It has been infinity all along. For the first time we're reaching J. Now the cost of reaching I was 9. So plus 2, you will have 11. Obviously 11 is better than infinity, so we're going to accept it. So this is the only value that will change. The rest we just copy them from previous iteration, 11, 15, and now 11. As I said, the predecessor is F. Okay, the predecessor of I is where we got the 9, which is F. Okay, now among this, again, we have a repetition of minimum. We have 11 and 11. So we're going to take the one that is alphabetically first and minimize it. Finalize it. So there is no better cost of getting of reaching C, and the minimal cost is 11. So we finalize it. But here, as I said, the predecessor is neither I nor B, it is F. So the predecessor here is going to be F. Okay, now make C to be your next active vertex. If you position yourself at C, you will see that C actually is a dead end. You cannot reach anywhere from C. So nothing will change in terms of the other values. Just copy them directly from the previous iteration. After finalizing C and putting the predecessor as F, just copy 15 to the next column, also 11 to the next column. Okay, the smallest value here is 11. Finalize it. Okay, the predecessor is I. So we're going to have I here. Now position yourself at J and see where can you reach. From J we can reach G. And interestingly, it's going to be a better cost because it is costing us 11 to reach J. And we only need to add 1 to reach G, so 12. 12 is better than 15. So this is going to be changed to 12. Okay. Right. So this is what we have. Okay. We have put the predecessor for 11. For J to be I, as I said, and this is our new value. It is the only value, so it is the smallest. Okay, so we're going to finalize it. The predecessor obviously is J, so we're going to have J here, and we're going to position ourselves at G, but we will see that at G we have nowhere else to go. Okay, so at G is also a dead end, so there is nothing to do, and therefore we are done. It seems by mistake a cycle is removed from here. Yeah, okay, it's back. Okay, so this is basically the solution. The next thing is to draw the resulting graph. Now I'm not gonna do this one by one as I did in the previous slide. I think it is very clear. Basically, we're gonna have the same vertices, okay, and then to get the edges, you will draw from the predecessor to the vertex. Okay, so I'll just show you the final graph. Okay, how we got it, as you can see, there is D to A, so D to A. And the cost was 4, so 4 is there attached to A. This is saying this is the cost of reaching A. Okay, then there is F to B, so F to B, okay, and the cost is 9, so you can see the 9. Okay, there is also F to C, so there is F to C, and the cost is 11, so you attach the 11 to the C itself. This is the cost of reaching the C. Okay. The starting vertex D has no predecessor, so just put the cost as 0. Then there is an edge, AE. So AE. And the cost of reaching E was 5. So you have to attach it to the E. Not to the edge, but to the vertex. Okay. And then there is EF. Okay, so EF, this one, E to F, there's an H there, and the cost of reaching F was 8, so you attach it to the F. Then there is JG. Okay, so JG, yeah, this is J, so JG, this H is there, and the cost of reaching G is 12. And then there is DH. So there's DH, you draw this edge. The cost of reaching H, of course, is 1. And then there is FI. So FI, this edge, the cost of reaching I is 9. So you draw it. And then finally there is IJ. Okay, this is IJ. So they look both as I, but actually this is I, this is J. So, and the cost of reaching J was 11. So this is how you obtain this resulting graph, just by drawing an edge between the predecessor to the vertex. And this brings us to the end of this example. I suggest that you take a pencil and paper and try to do both examples manually. If you can do both of them, then you will be sure that you understand the shortest path algorithm. This is the end of this first part of the graph lecture. I will still have another lecture that explains the Java implementation of graph. Thank you very much.